first came to NEAT Fair in 2003, and my background is I was born not far from here in Terrytown. It's right off the Hudson River.
Hey guys.
Hey guys. Paul. Button it, please.
And parents moved us out to Southern California when I was a year old, so I grew up in basically Santa Monica. And let's see, did a lot of plastic models. Both of my parents were artists. My dad did technical illustration for aerospace, and he would build a plastic model of an F-111, do really beautiful, and would use it as a guide to doing isometric and exploded views for like manuals and things like that. And did Gillows planes for a while, but the main thing for me was in junior high school in Brentwood. We had an elective class called Exploratory Aviation taught by a history and French teacher. His name was Bill Warner, and he was an author, wrote a lot of magazine articles on pre-flight modeling. And he had this class, an elective class, you could do that or metal shop. This would be 1978, I was 13, and basic model airplane design, but from a very hands-on kind of common sense approach, very little Bernoulli's principles and stuff like that. The funny thing, he was a drill sergeant, and he was really cranky. And he hated RC. He just disdained, had just hatred of RC. But any free flight, any crappy little free flight thing, he just fall in love with. And he did beautiful models. He would do like a Taube, the German early, just fully rigged out with the tissue and fly beautifully. Went out to contests, and we would have flying meets at our junior high school gym every couple of months, and Walt Mooney and Ken Johnson and all these free flight greats would come and fly, and we would have our little Roseanne planes and learn things. And that's where I got interested in doing the small planes, peanut scale and then grape nut scale. There were smaller ones, pistachio, yeah. And I was doing control line 049s, some 020s, and trying to do RC, but not telling the teacher. And I was embarrassed, so I didn't ask for help, and I was doing a lot of crashing. But eventually, hooked up with an uncle who lived down in Anaheim that did team racing in the 50s, and he was interested in doing RC, and he helped me out. And just being methodical, he wasn't an RC guy, but he just had the right frame of mind, and he got flying good. Then I got a job at a hobby shop, Pacific Palisades, and the owner there was pretty old, and he needed somebody to help carry stuff. We went out to the slope for slope soaring, so I learned how to slope soar. And then I started getting interested in the small slope soars. Got a Canon radio, saved up some money, three channel to work with my Futaba transmitter, and made some small slope soaring gliders and some small 049 and 020 and then 010 RC models with the Canon system. And let's see what else. And then I just did that, did some robotics, went to school at UCLA, got a physics degree, and went down to Miles Square Park in Fountain Valley, California, to hook up with my old teacher. This is, after I was in college. Met him up there, and met somebody from AeroVironment, and he said, I should apply for a job at AeroVironment. I had no work experience in aerospace. I was doing photographic equipment, embedded microcontrollers, 8-bit microcontrollers, programming in Forth, and doing some circuit board layout. But anyway, he said come and, apply. So I applied at AeroVironment, and then got the job there, basically hired on there to do micro spy planes for the Army for DARPA. And
didn't your job interview involve bringing small airplanes along with you?
Yeah. So I had one of those little folding luggage cart trolleys, and I think I had 2 loads of boxes stacked up that I brought peanut scale P-51 Mustang was all sheet wood. It was, I think, the Paul Mance red. P-51B that I did a really nice job on. I had 3 radio controlled blimps and my helium tank that I brought in, so I inflated those. And they were really wacky because I was into the pick chip programming, so I would, like Martin, have like a bazillion little combos of buttons and things, and it would had a blimp that had bomb bay doors and a winch and lights and searchlight and automatic ballast drop. It was all just kind of clued, but it was interesting, and I brought it for the interview. Had a little flying rubber band powered toy helicopter rocket. And basically, I just got hired on the spot, even though I had no aerospace. I had circuit board layout experience, electrical engineering, and the programming, and that's kind of what they needed. But also the whole the small aircraft stuff, because they were going to start proposing to DARPA to do 6-inch size spy planes, and that's what I ended up doing. And eventually that led to the Hummingbird and then the MarsCopter. But that'll be covered in the slide. So why don't you do your background? Ben Pipenberg.
Yeah.
What?
Oh, the dragonfly that you flew through? Yeah.
Yeah, no, I did a couple proposals for dragonflies, for mechanical dragonflies. And so anyway.
Sure. So Ben Pipenberg. I probably met a handful of you first time 20 years ago at the flood. I've been building model airplanes for most of my life. Grew up in Ohio, right outside Wright-Patterson Air Force Base, so right under the approach. Saw a lot of cool stuff coming in. That's kind of what got me into airplanes. Moved to central Pennsylvania when I was 8 or 9 or something, and found a really good mentor like Matt at the local RC club, who got me into glow-powered stuff. And at some point, I saw a little micro 238 or something in model aviation.
Oh, I read P38.
Red P38.
That's pretty good. I flew that here.
At the NEAT fair, that's right. It's probably around 2003, something like that.
Yeah, I had it here like 3, 4, and 5. I think,
Right. Yeah. So, anyways, that was kind of what got me interested in micro airplanes, seeing Matt's airplane in model aviation. Don't know if I told you that actually. Probably didn't. But started trying to find information mostly on the internet, how to build these little things. Right. Found RC groups, found the NEAT fair, and had my mom drive me out here when I was 13 years old, 2004. And so that's when I met, a lot of folks here, and kind of really got interested in building micro models. I don't think I actually met you in 2004 because you were stuck in a shelter.
Yeah, this was all flooded. The field was flooded. The motels were flooded. And we kind of randomly drove little groups. And we ended up in different gyms.
Yeah, right. And I think I met Henry and a handful of other folks, and Henry got me, kind of interested in doing, I would say maybe a little more high quality, very, very micro, sub-ground
You
airplanes.
got too micro from me, so I quit.
Oh, well, you were the one that got me interested in world record stuff though at the time, so thank you for that. But the next year I met Matt, and Matt told me that, you don't have to do engineering in school, you have to learn design, which was actually really good advice. I went and got an engineering degree anyway, but joined Matt at AeroVironment as an intern for 5 summers.
Probably our youngest intern. Because we would normally not hire interns like that early. But I knew.
Yeah.
You want the training right.
I knew he had talent. He would help us.
Well, yeah, I could still see the micro stuff.
Yes,
Give it 20 years.
But anyway, I would say that I learned kind of the basics and the technical stuff in college, and I learned design from that. Right? That's much more difficult to teach, I think, is the design side. So, and then after school, joined Matt at AeroVironment full time.
How many summers were you an intern?
I think it was 5 summers.
5 summers.
5 summers as an intern, and then came on full time.
The joke was, how many senior AeroVironment engineers would we have to get to replace a summer intern leaving at the end of the summer. It was usually 3, because he was super fast and efficient, and just worked through stuff. And the older guys were kind of like slow. I don't want to. But
Once you start getting paid, there's no motivation anymore.
Yeah, you kind of peaked out on the pay curve, but it was his summer internships were awesome. And one of his hummingbirds, I believe, is on display at the Los Angeles, California Science Museum, and it was one that he had to build because we were in a panic to get a milestone for DARPA, and Ben and I decided what to do, and he built it. It was awesome.
Yeah, it was fun. Those were a lot of fun.
So fundamentally, I met Ben through NEAT Fair, through the micro seminars. He hired on to AeroVironment because of the NEAT Fair and the micro seminars.
Yeah, exactly.
We did the MarsCopter together. We were both chief engineers. I don't know how or if the MarsCopter would have happened if we hadn't met up. If the NEAT Fair and the micro seminars hadn't happened, not sure.
That's amazing.
Isn't that weird?
Yep.
That's true. That's super neat.
And I came to the NEAT Fair under protest. I didn't want to. I don't like traveling. But Sergio Zigras just kept emailing me and calling me and said, "Oh, that's nothing. California. I got a guy coming from Norway. What are you complaining about?" I was like, "I don't know. Come on. They read your articles." And Sergio was awesome.
Yeah.
And he got me to come out, and it was great. Okay, so let's dive into the presentation on the Mars
Just
helicopter.
where the video photography stops.
Well,
This is all public at this point.
well, the only, if we want to be candid about complaints about JPL, we don't want to
Oh.
film
Yeah,
that.
we'll stop it.
I mean, let's just do the video. Well, offline we can do stuff, because like Tom Hunt was interested in seeing this, and he said he'd really like to see the video, so
We'll keep it going.
keep it going.
Okay.
Okay, so a little bit of, I'm going to do the background for the company AeroVironment. It's like aerodynamics and environmental systems is what the original origin of the company. And the main founder was Paul McCready, but there were actually a couple other, Peter Lissaman and another fellow, all PhDs, aeronautical engineering. And it was based on the human-powered, the pedal-powered airplanes
Oh my.
of the 70s and the 80s. And Paul was a sailplane pilot, and he invented the McCready ring, which is still used for sailplanes, for flying distances.
Mm-hmm.
I don't really know exactly
Speed to
what
fly, yeah.
speed to best speed to fly. So this is a little ornithopter that I now have that Paul was given, and you would use for demonstrations. It's a 4-wing canard pusher ornithopter built by Warren Williams. But that's a typical thing that when we would go and do a talk, like I did a TED conference with Paul. I was on the stage. It's on YouTube, and we'd go to Disney and the Adventurers Club with like David Attenborough and all these people in tuxedos, and we would be flying these things, and I'd fly my whatever my latest micro thing was, whether it was my personal micro or the work micro, we'd fly it at these things. And Paul was always coming by and showing me what he was doing. He wanted to see what I was doing. It was kind of the cutting edge. Some of the other things, AeroVironment, the association with General Motors. General Motors owned like 10% of AeroVironment for a long time, and we helped them design and build and operate the Sunracer car. That was the first cross-Australia race, solar race, and they won by a day or two. Second place was way behind. Like GM just threw tons of money at it, and they had a backup car and had like a whole train of support vehicles. Anyway, cool stuff. Lightweight structures, efficient electric motors, efficient use of power. Very much went back to the pedal-powered airplane. Everything is minimal, just what's needed to get the job done. Helios 2001, first propeller airplane to go to high altitude. So that was in the early stages of the design when I hired on. and that was being built in the same shop where I was doing the early 6-inch spy planes and later the Hummingbird.
That was solar powered, right?
Yeah, so it's all solar cells, and these are rigid solar cells, little tiny ones that are all tiled, going across there. We're building a similar plane now for a Japanese customer, so we're still trying to make that a thing. It's a tough business. Jumping back in time, Paul McCready, he was talking, I forget there's a story about how this came about, but getting funding to make a robotic pterodactyl. I mean, with realistic fur and actually tracking with the head. So if you were to make a glider this shape, what's that going to do? If you just made a balsa wood glider with the head and you threw it, what would happen? It would probably go backwards,
Yeah, it'd go
and flip
backwards.
and crash.
Yep.
So it had to have an early autopilot. So this is one of the first AeroVironment drones with a type of digital autopilot, and that head would just be flicking left and right based on I think a gyro, and it had the nostrils on each side of the face were differential pressure sensors. Yeah, like a pitot static. And then my kind of well-known project, again, Ben was summer intern, was the Nano Hummingbird, funded with your tax dollars, $4.5 million, 4 years. And it was more R&D than making an actual drone to be used. And it's about that tall, and the wingspan's about 9 inches. It was meant to be 3 inches, but we couldn't get it flying that small with the amount of time and budget. But really beautiful machining. This assembly right here, this is kind of the guts of it, and that's, it's about that tall. So very, very tiny gears. So we machined most of these gears. The tan is a plastic called PEEK, P-E-E-K, and it's a high performance, like medical grade plastic. It's really high temperature, has good properties. And then the silver is 7075 aluminum, and that was all machined in my lab that I set up. AeroVironment did not own any CNC thing at all when I hired on, not even a cheap 3D printer. So the first CNC AeroVironment bought was a Shoreline with hobby stepper motor running off of a funny dongle, and a printer port of a 486 computer.
Matt, can you talk? You're skipping over some of your earlier stuff. You did the Black Widow. You were featured. There was a Alan Alda Scientific American Frontiers that was like half about you, and I believe that you, through your grant, were able to partially fund in the development lab that developed lithium polymer cells and get lithium cells for the Black Widow years before we did. I mean, you just blew past all that, like with the Hummingbird.
Yeah, but Tom wanted to start the noontime show at 12.
Okay, all right.
Anyway, yeah. So the Black Widow was the big 6-inch spy plane project I did for DARPA, and that had half-gram servos. And they were basically built in Switzerland to our specification. They had a linear pot feedback. We didn't know about how to operate them. For idiots. And it had 2 PIC chips, one for flight controls and the other one for all the motor controls, the 2 servo actuators and the main motor. It had a black and white little video camera, a small little chip that we made our own housing and lens holder. It had a piezo gyro initially, just the one axis. It had pitot-static for airspeed hold and also altitude hold. It originally used NiCads when it was kind of really simple. So it used 4 50 milliamp hour cells, and then 4 100 nickel metal hydrides, and then we went to like the more formal battery pack, which was 3 lithium thionyl-chloride primary cells that were single use and had to be preheated. So we actually had to design a heater into the aircraft. and it preheated the batteries. And those batteries have chloride in them. One time we crashed it in the field and the thing was smoking and it was putting out chlorine gas. And I had to deal with it. It was just a park. In the old days we just would fly to local park. So I'm like inhaling chlorine and I had to go to the hospital. It was all a big thing. So
Stand up wind.
I can talk for hours.
Yeah, but
on
that
this
was
one
pretty
little-
early stuff.
What was the other thing?
Cocoa.
Oh, the batteries. Yeah. So
Batteries.
we did another early project with the spy plane was a little disc flying wing. Another one was a microbat, which is ornithopter, flapping wing, but forward flight. This was before the Hummingbird. And that originally flew with a rubber band, then it flew with a supercapacitor, then it flew with a single 50 milliamp hour NiCad with a switching booster to get it up to like 3 volts. And then we heard about lithium polymer batteries being developed in New Jersey at Rutgers, maybe? And we got a hold of the engineers there, and we were able to order tiny lithium polymer pouch cells. They were blue, packaged for $2,000 for like a 100 milliamp hour cell. And it was just like, there's no guarantee. You're gonna get a bunch of cells. Some of them may not work at all. Some of them might last a week. Some of them might last longer. And we were able to fly this little, like, I don't know, 10 gram microbat, with these early lithium polymers in 2001. No, 2000. Yeah. And get like, I don't know, 10-minute flight or something. It was pretty insane. And then at the same time, we were then taking that Black Widow and also seeing what we could do with the lithium polymers. But it ended up being stretched out, became the Wasp, and that became one of our smallest military drones. But it's too much. Okay, let's. But if there's anything you want me to touch on.
No, those are, I mean, like.
Okay, so most of you are here to hear about the Mars helicopter project. So before we dive into it, just so you know, a Mars helicopter has been operating on Mars for 2.5 years. It's a 4-foot diameter coaxial helicopter, and we're going to talk about how it came about and what our parts were in it, what our participation was, and what the operations were, and what ended up happening in the end. So, all right. Okay, why don't you take it from here?
Yeah, sure. So, how many of you were at our talk here 5 years ago? Out of curiosity. Oh, okay. So less than I thought. Yeah. Okay. So Mars helicopters. Basically, right now, or traditionally at least. Thank you. My slideshow here. Yeah. Good model.
Well, this way you can see it too.
That's true. So yeah, traditionally there have been kind of two main ways that we, as in humanity, has conducted planetary exploration, right? We have satellites that orbit planets, orbiters, which give you kind of the Google Earth view, right? They give you sort of 1 meter to 5 meter resolution pictures of the planet. And then you have rovers or landers, right? Things that get down onto the surface and you can get really good close-up science, right? Take pictures of rocks, get instruments on the ground, but they're very slow, right? You can only cover a very small amount of a very large planet. And so for a long time, since I guess early 90s actually, NASA's been talking about helicopters, right?
Or flying
things on other planets, right? Airships actually, I think, go back to the 70s or earlier. But the helicopter has kind of been around in fits and starts since kind of the mid 90s. Let's see, where does this go from here? Oh, so yeah, basically the initial start of this thing was like 1996 with some NASA proposals, and then when Matt showed, oh yeah, actually, is there an easel around?
Oh, yeah.
Oh, thanks. Yeah, that's good.
Just when we hold up the next one, we can put this one up.
Yeah, good idea. When Matt showed some folks at JPL, I think it was Bob with the Hummingbird in 2000.
Yeah, my
whatever
lab that I
was.
set up was a popular tour stop when we had visitors from anywhere.
Yeah. So when Matt showed off the Hummingbird to some of these visitors, it sparked a little idea in their brain, and it kind of reignited this helicopter idea because they realized, hey, technology is starting to get to the point where maybe this is feasible. And so that was kind of the nexus of it, I think, in about 2012 is when they first started getting involved.
And we had some background with a Mars airplane, a glider, for the Wright brothers centennial, and it was a folding thing that would enter in the Mars atmosphere and just do one flight. But it kind of got in some competition with Langley, and it all just kind of fell apart. A lot of politics.
And NASA.
So we did have, we already had a little bit of a taste of, working with NASA on space. But we'd already been working on NASA with the big solar plane. That was for NASA Edwards, which is now Armstrong. But talking about some of the challenges.
Yeah, right. So what is difficult about this, right? Because obviously flying a satellite is relatively well understood. Getting a car on the ground is relatively difficult, but it's at least well understood from a physics perspective. But flying on Mars is pretty tough. First of all, the atmosphere is about 1/100th of what we have at ground level here on Earth. It's similar to Earth at about 110,000 feet, 120,000 feet, depending on the time of day and the time of year. And that presents a whole bunch of challenges, not just in terms of power required to fly, right? But also, how do you get heat out of something, right? If you're in a vacuum and you heat something up, you're not getting convective
Any
cooling.
electronics will overheat.
Any electronics will overheat. And that lack of atmosphere also has implications as far as, protecting your electronics from things like solar flares, right? So having an atmosphere here on Earth actually is doing an enormous amount for us, right? As I'm sure everybody knows. What's this?
We'll talk about aircraft that have
Oh,
flown in those
sure.
air densities,
Yeah,
jets
sure.
and rockets. And
Sure. So I think AeroVironment still holds the record, I think, for highest
Propeller
powered aircraft
Aircraft.
that's flown on Earth. And that was, what's that?
How high?
Oh, 96,863 feet, exactly.
Which is very close to Mars
Exactly.
surface
That's right.
air density.
Yeah, and some of the technology that was developed there, the airfoils, the propeller design algorithms, things like that, were directly pulled in for developing the Mars helicopters. So there was a lot of heritage that was pulled from AeroVironment's previous work, and materials and structures and those kinds of things as well.
Yeah, like SR-71 reported to fly, 85,000, U-2 70,000, MiG-25 went up to 123,000. Special F-104 flew up to 120,000. So it's pretty impressive.
Yeah.
This was a little just comparison of the size of the two planets because the gravity is different.
Yeah, gravity is about a third, a little more than 1/3 of what we have here on Earth, right? And so 1/100th the atmosphere, 1/3 the gravity. So lower gravity helps, but it doesn't help quite enough, right? There's still much higher power. The other challenge, obviously, is getting the thing there, right? Mars, it's a long ways from Earth. It's about a 9-month journey.
At the shortest.
At the shortest, when we launch. And it has to fit on a rocket, right? Or fit on a rover, really, which then gets fit into a spacecraft that gets fit into a rocket. And so the helicopter, there's some pictures later on in the presentation, but it's kind of glommed just onto the bottom of the rover here. And there's very little space there. We actually started off kind of on the side in the armpit.
In the fender
Right,
well
up
of
in the
the wheel.
Right. And we think that JPL basically stuck us there because, they didn't really think about it, and they thought, well, by the time we get to a real spacecraft, this thing's going to get canceled and nobody's going to have to worry about it anyway. And then they realized, we actually have to worry about this, and stuck us right on the bottom. And so,
Go to this?
go ahead.
Okay.
Yeah, getting there. So, the rover gets mounted into a spacecraft which travels to Mars, but getting out of Earth's atmosphere and getting into orbit just around Earth gets stuck on top of this rocket, right? This is an Atlas 541, and launching on a rocket it's actually a very, very violent affair, right?
Now this is not a human carrying rocket, because those have specifications to be gentle. The
relatively gentle. Yeah.
Well, I mean, it's a big difference.
It is
The
a huge
requirements
difference, yeah.
are quite different. So
That's right. So the design spec for most of the helicopter quasi-static launch loads, which basically means if you were going to be applying just a steady acceleration to this thing, what it would need to take in all directions simultaneously is 60 Gs, which is a lot.
6-0.
6-0 Gs. Right. So that's quite a bit. Yeah, that'll hurt you. Yeah. And so that's what's driving most of the structural design, plus some stiffness requirements for helicopter dynamics. But this was really driving a lot of the mass of the helicopter and a lot of the structure.
And the supporting stuff that holds the helicopter.
Exactly. Right. So I mean, everything's just shaking like crazy. Right. You're basically riding a controlled explosion into space.
We did that.
If you're staying just slightly ahead of.
Mm-hmm. Right. Yes.
Uh,
Hopefully.
I don't know if you want to talk just a couple words.
Yeah,
Temperature,
sure.
radiation,
Temperature and radiation.
More
so,
things that are problems.
Right. Right. So cold.
There's nothing to look at.
Gets cold overnight. It gets down to about negative 130 degrees Fahrenheit. During the day, it actually is pretty pleasant. It's about 70. But that temperature swing is really the problem, and especially going down to the cold side, right? Getting everything designed to handle that full range of temperatures across different coefficients of thermal expansion.
And Mars has like 4 seasons like Earth, but it's over a 2-year period. And the Mars helicopter wasn't designed to go through the full Martian set of seasons. It was just going to operate in spring, kind of pleasant. So it wasn't designed to keep itself warm through the Martian winter, but it ended up doing that. So it ended up freezing, but freezing you don't really say freezing because that's water freezing, and there's like no water. But it got down to this negative 100, 200 degrees Fahrenheit every night for several weeks, and it actually had to recover itself from that deep chill every night, and it did. So it was we over designed it, just by our good engineering practices, and so anyway. So going back to what Ben and I did. So I started out as the chief engineer at the beginning of AeroVironment's effort, and that was for kind of early developmental testing and prototyping and the first full-size prototype. And then Ben's expertise really kind of came into play and was more important than my kind of conceptual model management skills. So he became the chief engineer, and there wasn't really a day, it just kind of evolved over the years. But at the end, like, I wasn't doing anything, Ben was doing everything. So anyway, just wanted to mention that if you're wondering.
Yeah, and the team composition here. So AeroVironment, especially early on, was doing most of the hardware design, fabrication, testing, and JPL.
For this helicopter, we built 100% of this and designed it, ran some of it by JPL.
Yeah.
And actually, these are the earlier ones. We got this out of order.
Oh.
So.
Yeah. Sure. So this was kind of 2013. So this was JPL came to AeroVironment, and JPL, for those of you who don't know, is Jet Propulsion Lab. It's part of Caltech.
It was the rocketry club of Caltech.
Right. In the 50s.
That's what it was, and it kind of still is.
Yeah. And then they got a whole bunch of NASA funding. They started to work on both early satellites for the U.S., early rockets for the U.S., and then went more into like kind of the planetary exploration side. So Cassini, Voyager 1 and 2, all of those programs through JPL.
Just test elements. So talk about the first 3-bladed.
Yeah, sure. So these first vehicles, basically, there was skepticism from, I would say, maybe the non-science community that was involved in funding some of these ideas, that you could generate lift in a Mars atmosphere, right? The engineering says that it should happen, but you have to prove everything. And so these first tests, this one over here on the right is just a simple motor and control system on a fixed stand. So it's a scale basically. And then over on the left is a single
Well, it went
axis.
up, this
right?
went up and down.
Yeah.
This was more of a marketing thing. It actually,
Right.
but it's just a motor with a 4-bladed prop with a box. And this was me. This was me. Like, we can do something that's kind of a marketing thing, and it'll kind of go up and down in Mars atmosphere. This was done right before I was chief engineer. There was another engineer, and he bailed out. It's like, this is a crazy project.
Yeah.
But this first thing, custom carbon fiber rotor blades with foam core, and everything else is basically hobby stuff. So the rotor system and swash plate from a RC helicopter.
Yeah, T-Rex.
And then there's a load cell, so that it just measures force in one axis at the bottom. And this was just spun up in the small JPL test chamber.
They didn't have a tail rotor on
No, this didn't fly. This is just sitting
it.
there.
Just a model.
Mhm.
But it did vibrate badly enough that it destroyed the load cell. and that
Resonance.
happened like a year ago again. So don't always learn from your mistakes. Sometimes
Yeah.
spend money repeating your mistakes. So anyway, and then
And that one
And
on
then-
the left, actually, it looks like a coax. Those
yeah,
are
they're offset
co-rotating.
vertically, but it's rotating together. And this was like, what can we do? We had like no budget. This was trying to. We had the data here. Everything's gonna look fine, but the VIP, the executives at JPL is like, nah, it doesn't look. So we were trying to like make something like visually impactful,
Yeah.
and that didn't work. And neither did these, but this is what we did next. And this is where Ben was hired onto the project.
Right.
Because Ben had all this experience doing micro carbon, foam, balsa wood, electronics, solving problems, fabricating, things quickly, trying them out. So what we said, I told JPL, we'll just make the whole helicopter. We don't need to do all these test stands. We'll do it small, which makes it harder. But that'll be that much more impressive when it flies. Because I was doing a lot of toy helicopters. I had a product. I can talk an hour. Should we go off? Me and Peter Murin both did toy helicopters at the same time as. Anyway, so I felt we could do this
Yeah.
with Ben's help, making it lightweight, and then changing the gearing so the rotor spun 10 times faster, and it flew. It flies if you throttle down and fly it in one atmosphere in the lab. It should fly in the low density, but it didn't. I mean, it took off. They had no problem getting off the deck. But the little angles, these both had the little fly bars that are at 45 degrees, like the models and toys, helicopter. That did not work in the Mars atmosphere. So it just kind of was ballistically, it's on YouTube, you can see the video. Did you have a quick question?
What powered these?
So these, we had tethered power. They didn't want lipos in the test chamber because if that exploded, that greasy acid would actually plate the entire 100-foot tall, 25-foot wide chamber, and then that would be bad.
And these chambers that we're talking about, so like I said, 25 by 100 foot, they're like national historic monuments.
Yeah, like
because they're-
every major spaceship has gone through that chamber to get qualified.
and they have basically a bank of 25 17 kilowatt lamps
In the basement.
in the basement, bounce off a mirror in the ceiling, and then can illuminate a pretty large area.
Well, the whole dog can illuminate
The entire chamber, yeah, right.
and it's the light level of the sun, not on the surface of Earth, but halfway between Earth and the sun. Think how bright that is. And they have to do it at night because it powers down Pasadena.
Yeah. So anyway,
They're like
very
arc
protected.
lamps. Because they have to
What power
put.
did you use?
What's that?
What power?
We just use the power supply outside the chest chamber and ran wires in.
On the actual one that's up there.
Oh, we'll get to it. We'll get to it. That's about 3 hours into the talk. So stand by.
All right, goodbye.
So Ben did a lot of fabrication on this particular model here, and then this was another one we did. We had another tech, not an engineer, but a technician, but he was also
Very
very good
model
model builder. And because we didn't know what was going to work, there's slightly different versions of toy helicopters.
Yeah.
And neither one of them worked.
Neither of them flew at all.
But
well,
they
flew a
both
little
took
bit.
off the ground
Yeah, they
just
flew a little
fine, but neither one was stable. And there again, the video of one of those in the crash is on YouTube. So that was 100% AV designed and built and operated. So it was our responsibility that it failed, but it would have been our glory if it had worked. And so going along with that, again, they're trying to show the executives at JPL NASA that this is viable. That was not acceptable. It didn't work. So at this point, Ben is on board, and it's like we need to be more aggressively trying to do it properly. More budget. So now we are at a full-size helicopter of what we're talking about sending to Mars. And again, this is 100% designed, built, and operated by AV as far as this. And then there was a signal connection going outside the chamber to a JPL like rack computer. And talk about design and fabrication of these elements.
Yeah,
I didn't really have much.
sure.
Well, I had a little bit to do with picking the drive system. So this was kind of wacky. There's a new motor, brushless motor at the bottom, driving to a spur gear, and then that is connected to another spur gear, and then there's a pinion gear with a shaft that goes to the bottom spur gear.
To a reversing.
Through a reversing gear, which Ben's got a 1 hour story on the reversing gear, because that was interesting. But later on we went to direct drive brushless motors on each rotor, but at this point we were trying to kind of go with what we knew, which is gearing the rotor blades from a single motor that you just purchased.
Right.
Yeah,
Again,
that was a
that's
Steve New motor.
Yeah. Any
Okay.
you do.
San Diego.
Inrunner. And again, power was from outside of the
Yeah,
chamber.
Right.
So yeah, talk
Where's
about
the chamber?
Where was this chamber?
Where is it? Yeah.
It's in Pasadena. It's on JPL's
in La
facility.
Cañada.
Yeah. So, I guess backing up for a second, what we basically learned with these small helicopters here is that dynamics on Mars, I mean, it still follows basic physical properties, but helicopters work a little bit differently on Mars.
It's viscosity of the air, and this was a problem with the human-powered airplanes. When you have the Gossamer Condor that only weighed 50 pounds, 100-foot wingspan, you try to just roll that thing in the air. The air is like concrete, right, compared to the saran wrap that it's covered with. And Paul McCready found this out by making models and matching the density and the Reynolds number in his pool. And so the same is in reverse on
Yes.
Mars. The
Yeah,
air
I've seen
isn't
that.
there to dampen things. So everything is like free running,
Yeah.
you know, like when you out in space and you toss a wrench, it just
Right.
flutters around.
Right.
There's nothing to kind of stabilize it. So
Yeah. So this is sort of more, I guess, akin to controlling a gyroscope than to controlling an aerodynamic body.
the rotors are flywheels.
Yes, the rotors are flywheels, and along those lines, one of the things that we learned is that this whole system needs to be very, very rigid to be controllable. So typical helicopters, right, you have a flap hinge, you have lead lag hinges. This thing has none of that. It's completely rigid, a completely rigid rotor system. We're trying to get our flap frequencies high enough that rotor dynamics basically were just rigid body kinematics. And so carbon fiber everything, very high modulus carbon fiber all the way through that system. Ceramic bearings, we could show some of that, but very, very rigid rotor system. And this first helicopter was just
Blade
to
and
demonstrate. Yeah, so blades and airfoils, carbon with machine cores all molded. But it's very similar to
Gossamer Albatross,
Gossamer
propeller, and Larrabee.
Yeah, it's using minimum induced loss.
What was his first name and where's he?
So there,
There's a
depending-
number of Atkins.
yeah. Larrabee and Atkins, and depending on whether you're British or American, there's an argument over who invented it first. But it's basically a very similar algorithm.
And you get the shape of rotor
Used.
blade, propeller or rotor
Yeah.
blade. It's super efficient. And the airfoil used on this was an AeroVironment developed airfoil.
Yeah,
Bart
it's-
Gibbs, who was our senior guru for the high altitude planes.
Right, exactly. And so this was basically developed to demonstrate that, hey, you can control one of these things in Mars' atmosphere, because we hadn't shown that up to this point. And so this was all designed, built at AeroVironment in about 5 months, and then tested.
Some stock carbon fiber tubes where we could. He
Right.
invented
Goodman's case.
carbon fiber balsa wood end grain carbon fiber sandwich panels, and CNC those.
Yeah, those were, yep.
Yeah.
That was most of the primary structure.
It was, yeah.
There was a lot of, yeah.
The gears were big peak plastic tan gears, and then we machined those down to get like most of the volume out. Oh, and then we talk about when you take the volume and mass out of a gear and put power through it.
Yeah, right. Well, so this was one of the issues with thermal design, right? So this thing actually, it basically stores all of that waste heat that you're putting into the motor and into the servos, the electronics, and everything.
Whatever structure is there.
Yeah, it just stays in the helicopter because there's no significant convection out. There's no significant radiation.
Yeah.
And so the motor, for example, we actually have what we call
down
phase change material. It's wax, right, which is stored on the outside of the motor, and as the motor heats up, it melts the wax, and then that heat is being stored into that melted wax. It lets you run longer.
Yeah,
But-
a heat sink doesn't work so well. More or less, would just absorb a certain amount of heat. It wouldn't.
And it
The
just gets hotter and
fins
hotter.
really wouldn't be doing much because there really wouldn't be any air molecules going over them.
Exactly. And gears, of course, you have some efficiency losses through gears, right? It's pretty high. It's about 95% efficient, but that 5% loss,
So,
where does that go?
like all
Right? Turns into heat.
all
And
the
so-
power is going through this first little gear here.
That's right.
Just for example, think about the number of watts mechanical power going through that tiny little plastic gear.
Right. And so, pretty.
That's the real thing. I mean, that's the Mars over there.
No, this is an early demonstration.
It's a full. This is the
Full
size of the
size.
real one,
Yeah.
but
Okay.
this was not. We didn't send gears to Mars.
Yeah.
Okay.
Yeah. And in part because of this reason. So that
Here that
first
we
time that we put this on the test stand and ran it up to full power, full thrust.
Yeah. Like take off.
Yeah, and ran it for any significant amount of time. That gear just melted. Teeth melted right off of it.
Did you guys have an idea that you were going to ultimately end up with outrunners, but you knew
Yeah,
that you
yeah,
had to
we
get,
did.
Yeah.
we need
Exactly.
to spin these
Yeah.
blades and just demonstrate this
Yeah.
work, but we know gears are not going to Mars.
Yeah.
Right. So if you
Okay.
go to this original concept art that we did, it's direct drive.
Yeah.
Okay, so
Yeah.
you knew where you were headed,
Yeah,
but
yeah, yeah.
but you got to demonstrate stuff to the big
demonstrate
wigs.
stuff.
Yeah.
Exactly.
Okay.
With a limited budget, limited schedule.
Yeah. Okay.
And there's no way we could have bought any outrunner at this time that we could have cut apart and fit on there. It just was,
Okay.
Maybe, yeah. I mean, maybe we could have. We've done that since then, but back then, yeah, it would be nice to go back in time and
Yeah, right, right.
rethink
Now
it.
with what we know.
But
yeah.
we went with kind of what we felt comfortable doing.
Right.
Cool. So that. Oh, so did this work?
Oh yeah. So okay. Right. So long story short, yes. This flew great. We got
Perfectly.
exactly what we needed out of
First
this
flight.
flight. Yeah.
Oh, the feedback was little 9-axis IMU that was on our circuit board on here. The data going down an umbilical, but then also, does anybody see little weird balls all over this thing? It's not. Anyway, those silvery gray balls. Does anybody know what those are for? Somebody's gonna know.
The performance, like this.
No. Yeah. It's called motion
So
capture.
you're able to see the air moving and.
Well, you can see the thing moving
Yeah. So,
itself actually.
It's
so
like
they
when
make
the
all
actors
movies
run
and
around on stage with all those balls
okay.
glued on, and they can do that, and then they can translate that into a monster, airframe. So we use the same system in the test chamber because although we had gyros, accelerometers, magnetometers, that would not keep it within a couple feet because the test chamber it was flying in really only had 16 feet of clearance, and it's a 4-foot rotor. So yeah, we needed a system that would actually have an absolute reference. And there was also a safety tether that I operated and I designed where I could have a throttle and I could pull up on a line, and there was a tether on the bottom. So if it took off, oh, this is why I have this little guy. So with the little short tether on the bottom, if it took off, it immediately started going to the side. I would pull up, and then it would bring it up and into the center, and then we could, shut it down and lower it without having to go into the chamber. Pumping the chamber down, it takes hours. So you want to be able to do any troubleshooting without breaking. What do they call it? Breaking chambers. What they call it? Yeah. Which is breaking the seal of the chamber.
Yeah.
So this worked great.
Yeah.
I mean, the YouTube video, and this is the one on YouTube, is super loud. It sounds like a Harley Davidson. And that's because of all these gears.
Yeah. And one of the important aspects of this thing was demonstrating that the controls team, which is mostly JPL, but also NASA Ames, would be able to, basically characterize this thing without ever flying it, and then just hit go, and it would take off and it would be stable, right? Because that's what you have to do on Mars. And so that actually completely worked. First flight, just hit the go button, and it took off, hovered, and landed.
And that's not to our credit. That was to JPL's credit of really doing the analysis and simulations and the software checkouts. That's where I think that's where Ben and I really gained a lot of respect. These guys are thorough and they know what they're doing.
Yeah. Not good
And we ate a little bit of that back later on because some other things happened.
Yeah.
But at that point, we thought they were golden gods, basically.
Yeah, right.
This is the next slide. I don't know if that's appropriate.
Yeah, sure. So after this first helicopter, now it's getting into how do you design this thing to actually go to Mars. So there were two what we call the engineering development models. One of these was for environmental testing, to making sure that it will survive vibration, shock, right? So those are the rocket loads, the cold temperatures, radiation environment. And then the other one, the second one, was primarily used for flight testing. So this was called system identification. And so there's a whole series of different test rigs that this thing was mounted on. So starting from just basically putting it on a glorified scale, right, measuring moments on all axes. There was a big swinging arm that it was mounted on to simulate forward flight. There were a bunch of different gimbals, so you could unlock one axis at a time, essentially. So get one axis stable, get two axes stable, and then get all three axes stable prior to actually trying to fly the thing. So that was used to develop the autopilot and the flight control.